Atomic structure and theory. This is something that we should have a very high level of familiarity with, but I want to make sure that I review a lot of the details that you need to know about atoms, their structure, and the theory behind it. Okay, so for atomic structure, you should know that protons are positive, neutrons are neutral. You should also understand that electrons exist outside of the nucleus. The nucleus is small, the nucleus is dense. It has most of the mass of the atom, whereas electrons do not contribute very much mass to the overall mass of the atom. You should know that the atomic number, which is given as the bottom number in nuclide symbol notation, equals the number of protons, which also equals the number of electrons for neutral atoms. You should also understand that the mass number of any element written in nuclide symbol notation is simply the sum of the protons plus neutrons. In this case, carbon-12 has 6 of each. Isotopes are different varieties of elements that have different numbers of neutrons but the same amount of protons. Almost every element on the periodic table has various isotopes that make it up. Those isotopes occur in nature by some predefined percent abundance. So if you scoop up a pile of carbon, you're going to see about 98.9% of it is carbon-12, so on and so forth for each isotope. Isotopes are similar to each other by the number of protons. They're different by their number of neutrons. I'd like you to pause the video and take a second and see if you can construct 2 stable isotopes of nitrogen. This is a good opportunity to play around with this simulation, which should give you a good sense as to where the protons are, where the neutrons are, where the electrons are in relation to each other, and then also the ability to express 2 different isotopes of nitrogen. Okay, well, I hope you have an opportunity to go ahead and do that. I'm going to move on here to atomic mass. Atomic mass is simply just a weighted average of the masses of the individual isotopes of that element. So when we talk about the atomic mass that is shown for oxygen on the periodic table, if I'm looking at the periodic table that I have hanging in this room, the overall average atomic mass is 15.9994 atomic mass units. Now, it's not going to be equal to any of the individual masses of these isotopes. These individual masses are unique to these isotopes, and each isotope is a certain percent abundant, just like your grade in class is calculated by, 50% of your test, 50% of your classwork, multiply each of those grades by those percentages expressed as decimals, you get your overall grade. The same holds true for the average atomic mass for an element. So this is just showing you how average atomic mass is calculated. Using the information in the previous table, I can substitute those values in, and I can round my final answer to get the mass that should show up as that bottom number for oxygen on the periodic table. That bottom number is not the mass number, it is the atomic mass. It's the weighted average of the masses of all the isotopes. This is completely new to you. Mass spectrometry. Mass spectrometers are devices that are used in order to analyze the masses of different particles that are shot through them. They have a magnet that deflects the charged particles that are charged here with the electron beam source. And then depending on how heavy they are, the heavier they are, the less they move, the lighter they are, the more they move, and the detector can distinguish their masses very easily. That was a very quick overview, but there's a YouTube video that I'm also going to attach to Canvas that goes through how a mass spectrometer works. So I'm going to ask that you pause the video, watch that YouTube video real quick, and then come back to this presentation. The one thing you need to know how to do is how to interpret what a mass spectrometer gives as its reading. So for instance, can we tell what element this is? Well, for instance, I can see that there are 2 isotopes being separated by the mass spectrometer. Isotope 1 has a mass of 10.0129 atomic mass units. Isotope 2 has a mass that's a little bit above 11. I also have their percent abundances, which is given by the y-axis of these mass spectra. So if I go to my periodic table, I can make the assumption, yeah, this must be boron, because if I take the information from this chart and I take that and I substitute it in to my atomic mass equation, I can figure out that this atomic mass matches that of borons, and therefore that is the mass spectra that I would expect to see should I introduce boron to a mass spectrometer. This was actually an AP free response question, and it has you estimate the average atomic mass of livermorium to 4 significant figures. So I'd like you to use this mass spectra to estimate the atomic mass of livermorium using this chart, similarly to how we did in the previous problem. I'll give you a hint. You have to use the y-axis to estimate the percent abundances. Take a moment, pause the video, and see if you can do that. So when I look at this graph, I can see that the masses are very clearly given to me, but the percent abundances are not. However, the number of atoms is given by the y-axis. So 2 total atoms in this sample had this mass, 3 total atoms had this mass, and 5 total atoms had this mass. That adds up to 10. So I can use those fractions, 5 out of 10, to say that 50% had this mass, 3 out of 10, or 0.3, had this mass, and 2 out of 10 had this mass. So that would be 0.2. Substitute that into my atomic mass equation, I can estimate its mass. These small details are going to come up on the AP exam. We kind of gloss over this information because this all should be background knowledge that we're carrying from honors chemistry into this class. We'll be heading into light and energy in our next presentation.